Good morning and welcome back to Dr. Logic Awkwardly Does Logic. I promised you a really cool result in this video, so let's jump right in and get started. So recall the definition that I gave you in the previous video of a modal constant formula. So this is a formula that is built up just from arbitrary tautologies, arbitrary contradictions, propositional connectives, and modal operators. So there's no atoms. Recall also the definition of the PL transform, which basically takes a formula and removes all of the modal operators. So if you take the PL transform of a modal constant formula, you will end up with something that has top and bottom and propositional connectives and nothing else. So no modal operators and no atoms. Keep this in mind because this is the starting point for this very interesting lemma. This is something that we can prove in system D, and so will hold for any system that extends D, but is not going to be true of any system weaker than D. So what is this cool result? Let phi be a modal constant formula. So only top, bottom, propositional operators, and modal operators. Then we can prove the following. First, that if the PL transform of this modal constant formula is itself a tautology, then we can prove the original formula in phi, in D. We can prove the original formula phi in D. Now, this result is not terribly surprising because we already know that all tautologies are already valid in their axioms, and so you'll be able to prove them in D. What's interesting is that it's the PL transform that is the tautology, so the bit without the modal operators, and so this first one says, well, you can add all the modal operators back in and you can still prove it. The second point is the one that is more interesting. So if we have something whose PL transform is not valid, that means that there is at least one model that makes it false, then in D, we can prove the negation of phi. And this is where the fact that these are constant formulas comes into play, because this isn't going to hold for just arbitrary well-formed formulas, because just as an example, the PL transform of an atom is just the atom itself. And we already know that no atom is valid because you can always come up with a model that assigns this atom false at some world. But it's also not going to be the case that you can prove in D or indeed in any consistent system this atom P. So the fact that we're talking about modal constant formulas is important here. So another way to put this is that if the PL transform of a formula is valid, then that formula is provable in D. If the PL transform of a modal constant formula is not valid, then you can prove its negation in D. So how do we go about proving this? This is going to be a proof by induction. We've seen a few proofs like this, but we will see many, many more over the course of looking at modal logic. What we mean is that we will look at the complexity of the formula. So we'll start off and say, okay, suppose that we have a formula that contains only constant formula, only constant symbols, so either top or bottom. And then we'll show that we can prove it for that. Then, assuming that we have kind of gotten up to a certain stage of complexity, so we've proven that it holds for phi and it holds for psi, then we will next show that if we add one more stage of complexity, so if we want to consider not phi or phi and psi or necessary phi, then assuming we've kind of already done everything right up to a certain stage, adding one more operation will not cause us to fall into problems. So this is the general kind of structure or strategy of an inductive proof, induction on the complexity of phi. So the first, we're just going to note that every constant formula is equivalent to one that is built up using so it's built up from bottom using only, negation, disjunction, and necessity. So this set is adequate to represent any modal constant formula. And what I mean by this is that suppose that we have formula top. Well, this can just be represented as not bottom. Conditionals can be defined in terms of disjunction and negation, conjunction as well. And we have that necessity just is not, possibly not. So there you have it. So this means that we only need to prove 4 different cases. This will be our basis case where we prove it that it holds for bottom, and then we'll prove it for each of these other ones. And then the case of conditional, conjunction, and possibility just reduces to these cases that we've already done. So we will, in this video, prove the basis case and the modal case. I'm going to leave these 2 cases as exercises for the viewers. So if you want to give it a go, feel free to put some answers in the chat and I'm happy to take a look at them. But this is a good opportunity for you to really start getting engaged with the definitions and see how it is that all of these little bits all come together and start working. Anyway, let us begin with our basis case. So the first case is where our formula is an arbitrary contradiction. Now, the first thing to note is that the PL transform of an arbitrary contradiction just is itself. And as I noted up here, the negation of a contradiction just is a tautology. So given these 2 things, it follows that the PL transform of a contradiction is not valid. And that puts us in the case of this second one. So now we want to be able to prove that in D, you can prove the negation of this. But since top is an arbitrary tautology, and as you recall, all tautologies are all axioms. So it is an axiom of D, and hence you can prove it in this, which is the same thing as saying that you cannot prove that you can prove the negation of bottom. So in the case of the atomic one, it's only this second thing that we can prove, because the first one is automatically true simply because the antecedent of this clause is false. So that's all that we need for our basis case. Now, for the inductive steps, what we're going to do is we're going to assume that 1 and 2 hold of some arbitrary formula phi. We want to show that 1 and 2, oh, I've got too many 1s and 2s. I mean, these guys up here. We want to show that these 2 claims also hold of necessary phi. So we're assuming that it holds a phi, and then we're going to show that it holds at one more step of complexity, necessary phi. Now we've got 2 possibilities. Either the PL transform of this is going to be valid, or it's going to be not valid. Let's start with the first one. So assume that, in fact, the transform of necessary phi is valid. Now, You might not remember exactly the definition of the PL transform, but I will just give it to you here. By definition, the transform of necessary phi is just the same as the transform of phi, because remember, we are just deleting modal operators. But if we have therefore assumed that the transform of necessary phi is valid, and that is the same as the transform of phi, we know then that the transform of phi is valid. But what is it that we assumed as our inductive hypothesis? We assume that if the transform of phi is valid, then you can prove phi in D. So by this inductive hypothesis, we have that in D, you can prove phi. Now, by the rule of necessitation, we can stick a box on the front. And that is what we wanted to show. Because we started from the assumption that the transform of necessary phi was valid, and we got to the fact that you could prove necessary phi. So now we need to consider the other case, which is where the transform of not phi is not valid. So now we will assume that the transform of necessary phi is not valid. Again, by definition, the transform of necessary phi just is the transform of phi. So what our assumption is that the transform of phi is not valid. Again, we can go back to our inductive hypothesis, which says that, okay, we're assuming that this second clause also holds for phi. So we know that if the transform of phi is not valid, then in D we can prove not phi. So by the inductive hypothesis, we have that in D we can prove not phi. Now, do the following proof. So we've got, we know that we've got this proof of not phi. This is given to us by the inductive assumption. Necessitation allows us to put a box on the front. The D axiom with a substitution of not phi in for P gets us that necessary not phi implies possibly not phi. So that's uniform substitution, not phi in for P in the D axiom. Modus ponens says we have possibly not phi from lines 2 and 3. And then finally, modal interchange allows us to change from possibly not to not necessary. So modal interchange line 4. And this means that we have shown that you can prove in D not necessarily phi, which is what we needed to show under the assumption that the transform of necessarily phi was not valid. You can use this case, the case of necessity, as a model for your case for negation. So you have the same sort of inductive assumption, you've got the same sort of steps that you go through. At the same point, you will appeal to the inductive assumption, and eventually you should be able to get your result. For conjunction, it's very similar, but you just need to do, disjunction. One more step in your inductive hypothesis. You just need to assume that it holds for both phi and for psi, and then you can put them together in a disjunctive format. So see if you can use this example, this kind of model proof step that I've given you, and extrapolate to the two other propositional cases. The one last thing that I want to just note here is this line right here. This is where we appealed to the D axiom. Without this entire result would collapse at the modal stage. So this is why this is something that we can prove in system D and in any system stronger than that, but we cannot prove in something weaker. So isn't that cool? I hope you found that fun and interesting. And I also hope you found the example of the inductive proof helpful, because as I said, we are going to start seeing a lot of these. So get used to the structure. So having a basis case, identifying the right inductive hypothesis, going through all of the cases, recognizing which cases you need to prove and which ones are just going to be equivalent to things you've already proven. Start getting into the habit of working with these types of proofs, because it'll make life a lot easier as we get to more of them in the future. Until then, take care, enjoy your inductivating, and see you later. Cheers.